Okay, friends, so here we are in day 2 of the normal distribution. There's our good buddy behind us. And as you've seen in the past day, it's incredible how many different things this curve can model in our lives. For example, suppose you want to model newborn weights of infants. And there you have it. You've got an average at 7.5 pounds, and then you've got your standard deviation of 1.3 pounds that we chatted about in class. And theoretically, babies can keep getting heavier and keep getting lighter, down to a point. Eventually they'll zero out. Okay, but suppose you're not interested in baby weights. Suppose you're interested in, say, IQs. And there you have it. You've got your average in the middle of 100, and then you've got your standard deviation going out 15 points. Each standard deviation, an additional 15 points. But suppose you're sick and tired of hearing about babies and IQs. Let's talk about Heartwood diameters of trees. And here you have it. The diameter of a hardwood tree's heartwood, which is that piece in the middle, average of 4 centimeters, and then up and down 1.9 centimeters from that. So what you're seeing is, the shape of the curve stays the same, which is rad. What changes is whatever's on the horizontal. The units can be in pounds or years or degrees or inches or whatever you measure. Generally speaking, it's going to be continuous with normal distribution, right? These are all measurements: centimeters, pounds, temperatures, weights, whatever you got. In fact, to get around the fact that the curve is the same in all these situations, and the only thing that changes is the horizontal, statisticians come up with a really, really slick way of simplifying it. And this is the axis they use. All right! This is called the standard normal distribution. And you'll hear it from time to time. It's used, as you've seen, the normal distribution is everywhere. I think that's why they call it the normal distribution. And just to give you a fun little historical fact, back when Germany used to actually use marks instead of the euro, their 10-mark bill had not only a mathematician on it, but the bell curve on it. It's Carl Friedrich Gauss, one of my favorite mathematicians of all time, and a bell curve on their money. What do Americans put on our dollar bills? Presidents. Useless. Anyway, point being, the normal curve is so ubiquitous, to simplify calculations along the normal curve, we use this measurement system here. Now, what's the unit on this? There are none. That's the best part. What does the 0 mean? The 0 means no standard deviations away from average. None. 1 is 1 standard deviation up. 2 is 2 standard deviations up. -2 is 2 standard deviations down. It's so logical this way. It's super nice. All you've got to do is be able to convert back and forth from whatever data you have into this unitless bit, which is a large part of what we're going to be doing today. So now we can focus on only the principles of the curve and the characteristics of the curve. Just to recap, the average, and you know what? The median and the mode are all pretty much the same thing. They're right there in the middle of the curve. They're all about the same number. There are certain percentages trapped within standard deviations. We've already focused on 3 main ones, 1, 2, and 3 standard deviations. We're going to do a lot more today. There's one thing that I glossed over yesterday, and I'm going to offer as optional videos if you want to watch them today. I'm going to put them at the end of this playlist. In any good probability distribution, as you remember, the sum of all the probabilities have to be 1. When you look at this curve, we already discussed the probabilities are the heights above this horizontal axis. Now, you may have been bothered a little bit by the fact that this curve doesn't look like it's touching the horizontal axis here, nor does it look like it's touching here. Theoretically, it never touches. Theoretically, that thing keeps on going forever in both directions. Realistically, it has to stop in certain data sets. For example, weights of newborn babies. Remember they kept getting smaller? Well, eventually, a baby has to weigh something. It can't weigh nothing, and it can't weigh negative pounds. But theoretically, this curve, the standard normal, has what are called asymptotes. This curve asymptotically approaches the horizontal axis here, and it also asymptotically approaches the horizontal axis here. Now, how can something have a combined area of 1 when it never stops. And that's something that I've explored in some videos at the end of this playlist, if you're interested. You don't have to be if you don't want to be. It actually breaches another subject other than statistics. I'm going to leave it at that. If you want to watch it, they'll be at the end of the day. But the big takeaways are, since so many things use bell curves, we're going to use these unitless measures down here to deal with that. And we're going to do the rest of today is look at lots of different kind of data sets I've collected over time and explore the areas in between these whole numbers. I think we've got the whole numbers down pretty well, right? Like between -1 and 1, we know that's 68%. Between -2 and 2, that's about 95%. Between -3 and 3, that's almost all of it, about 99.7%. But how about the areas in between? What if you go from like -0.5 to -1.5? What's that equal? Let's get into that next.